Now the next is based on where the atoms are. Remember the atoms, most of the times atoms will be on the corners, although in few cases, few atoms can be missing. But based on where the atoms can be, whether on faces, whether in the body, there are total 7 types of primitive cell units and total 14 Bravais lattices. What we call them? Bravais lattices. Cubic. In cubic, there will be primitive. Primitive means only corners. It is cubic. Okay? And there another possibility is body centered. In cubic, another possibility is face centered. You might think that why we are not talking about all these in other types, say tetragonal or hexagonal. Okay? The reason is that whatever is possible, what actually exists, that's we are talking about. We are not going to talk about just imaginary lattices. Here only those lattices are mentioned which actually occur, which are actually possible. So they are actually exist in nature. So that's why written here. So in cubic, tetragonal, orthorhombic, hexagonal, rhombohedral or trigonal, same thing. And then monoclinic and triclinic. The names you will have to memorize. You don't need to go into details. Obviously, a little bit detail I'll go into. But if you try to understand that concept, it will take 2 hours, but no question will be asked from there. Absolutely zero question that how these are formed. Okay. You just need to remember 3 or 4 statements and it's done. So you don't need to waste 2 hours. And actually you have only 2 hours per subject. That is again at the higher side per day. So if you waste 2 hours there, it will be just one day you lost. So don't waste your time here. Just try to memorize. There are cubic, tetragonal. We will be talking about these in detail, but only primitive ones. Okay? We will talk about these only primitive ones, and the rest ones, nobody is going to ask specific questions. However, you have to memorize these things. In cubic, and when I say cubic, it means its shape is of a cube. There are 3 possibilities: primitive, only corners; body centered means corner plus body; face centered means corner plus all faces. Cubic lattice will be that one in which all the sides will be equal and all the angles will be equal. And you know, if it is cubic, if you form a cube, in cube, all the sides are equal and all the angles are 90 degrees. So this is, you know, the only important point is that you need to remember the examples also because these are asked. Give an example. Sodium chloride zinc blend means ZNS and Cu, copper, are the examples. So you need to memorize these things. Then another possibility is tetragonal. And these shapes we will actually see by diagrams, okay? These shapes we will see. Tetragonal shape will have 2 sides equal. The third side will not be equal. All angles will be 90 degrees. It means it is actually cuboid. So tetragonal is actually a type of cuboid because in cuboid you have 2 sides equal. So say these 2 sides are equal. This side is different. So it is a cuboid. And all angles will be 90 degrees. You know that in a cuboid. Examples: white tin, SNO2, TiO2, CaSO4. Try to memorize these examples. Otherwise, at the time of examination, it will be very difficult for you to memorize and retain. And in Viva also, I will be asking these examples. So better you memorize right now. Then orthorhombic. In orthorhombic, neither of the sides is equal. Means it is again a cuboid because all the angles are 90 degree. Remember, it is again a cuboid. But in this case, this cuboid is like this. So A, B, C. A is not equal to B, not equal to C. But all the angles are 90 degree. A is not equal to B, not equal to C, but all the angles are still 90 degree. So these two are cuboids. The difference is in tetragonal, A is equal to B. In orthorhombic, none is equal. So in first three, you need to remember this is same. And in this case, as you move downward, first this becomes not equal. Then you again move downward, both become non equal or unequal. And remember, you will write B not equal to C. Don't write A not equal to B because by convention, the sides and angles are related. Next, hexagonal. In hexagonal, you know that one angle will be 120 degree. I'll show you the diagram because hexagon, if I consider the base hexagon, okay, base is hexagon, then all these angles will be 120 degree because hexagon, regular hexagon will be like this. All angles will be 120 degree. But these angles will be 90 degree. So this angle will be 90 degree. Okay, here. And this angle will also be, these two angles will be 90 degree. All these angles will be 90. So I'll show the detailed diagram later on, but for now, this should be sufficient. So in hexagonal, that's why one angle will become 120 degree. Remember, due to hexagonal, hexagon. And in base, A and B will be equal. That's why the angle will be 120 degree because it is regular hexagon. A is equal to B. That's why. Next one, rhombohedral or trigonal. All sides equal. Alpha equals to beta equals to gamma. Sorry, alpha. But none of the angles is 90 degree. Cubic and rhombohedral, I'll show you the difference that if you just push the cubic, if you just push a cube on one side, say this is a cube, and you push this cube from this side. So it will be something like this. Now, none of the angles will be 90 degree. So it is cube one when pushed from one side. All the sides will be equal, all the angles will be equal, but not 90 degree. Next, monoclinic. And remember these names, you have to write these names. Monoclinic, none of the sides equal. Two angles 90 degree, the other angle is not 90 degree. Okay, so this is sulfur, which is monoclinic sulfur, because sulfur we will talk about when we will talk about the allotropes of sulfur later on. Then sulfur is of different types, alpha sulfur, beta sulfur. Okay, this is monoclinic type, or rhombohedral sulfur, or orthorhombic sulfur. Triclinic is none of the sides equal, none of the angles equal or 90 degrees. So remember, none of the angles is 90 degree, and also they are not equal. So triclinic one is very easy to remember. Nothing equal and nothing equal to 90 degree. So effectively, you have to remember only two. If you see, only two will be difficult to memorize. Okay? The last one is very easy. Even monoclinic is easy because this none is equal here. Here, just one thing you need to remember, that alpha equals to gamma equals to 90 degree. Remember, that's why I said that you need to write in the sequence. You can't say that A equals to B. Here in this case, you can't say A is not equal to B equal to C. The reason is the sides and angles are interrelated, which is visible here. Although here we are saying none is equal, but still we are writing here alpha and gamma are 90 degree, but beta is not 90 degree. So it's again easy. Why it is easy? Because you just need to remember one thing. Beta is not equal to 90 degree. It means alpha and gamma are 90 degree, and those are equal. So that itself gives you a hint that alpha and gamma will be 90 degree and none here. So on this last two, monoclinic, triclinic, this is same. And in triclinic, nothing is equal and nothing is equal to 90 degree. No angles 90 degree. What is the change in monoclinic? The only change is beta is not equal to 90 degree, but the rest of the two are alpha and gamma. These three are easy to remember. If you remember the sequence, cubic, tetragonal, and orthorhombic, if you remember the sequence, the angles are 90 degree, nothing to remember. First, B is not equal to C, then B is not equal to C, and A is not equal to B. Easy. Rhombohedral is also very easy. All are equal, but not 90 degree. This one is slightly, you have to remember. A is equal to B, not equal to C. Alpha equals to beta equals to 90. Gamma is 120. So only hexagonal and monoclinic, sometimes students make mistakes. And that's why you will see the question is based on hexagonal and monoclinic. Mostly, you will see. I'm saying, remember the question, monoclinic and hexagonal, because these are difficult to memorize. So the question might be differentiate between hexagonal and monoclinic. It means you have to just write this configuration with examples of graphite, zinc oxide, cadmium sulfide, and here you need to write this configuration with examples: monoclinic sulfur, sodium sulfate. Now just the primitive ones. So as I said that we will be talking about only primitive ones: cubic primitive, tetragonal primitive, orthorhombic primitive, hexagonal primitive, rhombohedral primitive. monoclinic primitive, and triclinic primitive. Total 7. In total, there are 14 Bravais lattices. These are called Bravais lattices based on the name of the sign. But total are 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Major ones 7, but in total 14. So the first one, cubic primitive. Cubic primitive, there is a cube. All sides are equal. All angles are 90 degree. And you know the angle alpha is actually between A, B and C. Angle alpha is between B and C. Angle beta is between A and C, or C and A. Angle gamma is between A and B. So angle alpha is between B and C. Remember, opposite. Then tetragonal primitive unit cell, as I said, it is a cuboid because all angles are 90 degree and A and B are equal, but C is not. So tetragonal is actually cuboid with a square base. It is a cuboid with square base. Next, orthorhombic primitive unit cell. No side is equal. All angles are 90 degrees. So again, it is a cuboid, but with no sides equal. It is a cuboid, but no sides equal. Then we have hexagonal. We are talking about only primitive unit cell. Now, hexagonal, when we consider the angle, 90-degree angle is specifically, remember 90-degree angle is between A, B, and C. And here A, B are adjacent ones. A and B are adjacent ones. Then again here it will be B, and after that A, and so on. Okay. So A, B, A, B, A, B, like that. And we will consider the angle between A and B, like gamma. So this is A, this is B. Angle between A and B will be gamma. Now for angle A will be angle alpha, sorry, angle alpha will be between B and C. Alpha will be between opposite sides. So if you remember the unit cell I had shown to you, just if you don't remember, if we have A, B, C, then the angles will be opposite to A will be alpha, means between C and B, B and C. Beta will be opposite to B. Opposite to B means between A and C. Okay. Gamma will be opposite to C. Opposite to C means between A and B. So the same rule we will follow here. So beta will be actually between C and A. So alpha will be between B and C. So this is B, this is C. This is alpha between B and C. Beta will be between A and C. So this is C, this line, vertical line. This is beta between A and C. Gamma is between A and E. Hexagonal, I am just explaining a bit more because questions will largely be on hexagonal and monoclinic. It's not that questions can't be from other, but most important, these two. Rhombohedral primitive unit cell, as I said, that if you have a cube and you push it from one side, it will turn out to be rhombohedral primitive unit cell. Now it is A equals to B equals to C. So all are equal. A, B, C. You will see that all angles will also be equal. Between A and B, it will be more than 90 degree. Between B and C, it will be more than 90 degree. Between A and B, gamma. Okay, gamma will also be equal to alpha, greater than 90 degree. So all angles will be equal and greater than 90 degree. Not equal to 90 degree. Next, monoclinic primitive unit cell. Again, very important one. In monoclinic, none of the sides equal. So if you remember, this is the sixth one. Last two we talked about. So this is the monoclinic and triclinic. In triclinic, nothing is equal, nothing is 90 degree. In monoclinic, sides are not equal. Beta is not 90 degree. It means alpha and gamma are 90 degree. So that's what you will draw or you will identify. Yeah, you will first, if it is given, or mostly basically you will be asked to identify on the written values. But sometimes diagrams are also given to identify the type of unit cell. Normally you will get written like this. But if you get a diagram, you will calculate. Here there is nothing written that these are equal. So you will write A not equal to B not equal to C in the diagram. In the diagram, it is given that alpha and gamma 90 degree. Alpha will be angle between B and C, 90 degree. Gamma is between A and B. This is B. This is again 90 degree. But beta is between A and, sorry, yes, C. Between A and C. It is not 90 degree. So actually it is, if you need to visualize this one, this is that it might be considered as a cuboid like this. The angles were 90 degree, but what we did, we pressed it from this side. The moment we pressed it from this side, this angle became greater than 90 degree. Yeah, this angle became greater than 90 degree, but this angle and this angle remained same, 90 degree, and this also 90 degree. Only the angle in the base got different. So monoclinic is actually cuboid, but pressed from one side, not in both sides, one side only. So even if you're not able to visualize, this is important. You memorize these things. Triclinic, nothing equal, no angle equals to 90 degree. It means this is the cuboid which has been pressed from both sides, horizontally and vertically. So all angles got disturbed. Here we pressed just one side, then it was monoclinic. But if it is pressed from the top also, then in that case it will result in triclinic. Now the very important part, from where numericals appear. And if there is any confusion till now, my answer is you need to memorize all 7 lattices structures. You have to configurations you have to memorize. There is no shortcut for that. Now the important part, number of atoms, which is also written as NOA, and you can get it written in abbreviation in your exam also in unit cell. It means the same thing what we discussed in the previous class. How many atoms actually are in one cell? How many atoms are part of one cell? So for example, we talked about that at the corner, the contribution of one atom is just 1 by 8. But there are 8 atoms on 8 corners. 8 into 1 by 8, there was only one atom as a whole. So that's what we discussed, that this atom, actually, if it is on corner, it is just 1 by 8 in one cell. Okay. Total 8 cells have the corners, same corner, total contribution 1. Then we talked about body-centered cubic cell. It is inside the body. So remember, when we are showing the diagram, you might see that we are showing these just points. So that's why these are also known as lattice points. So this is just one lattice point. What is lattice point? If you are asked what is the significance of lattice point, that question is very common. You will say lattice point is an atom, ion, or molecule which forms the structure of the lattice, or which is at the corners of the lattice. Now, this is in reality what it will look like. It is closer to what it should look like. There are corner 1, 2, 3, 4, okay? And then fifth one will be behind it, which is not visible, 5, 6, 7, 8. This one is actually in the body. Okay? So the all 8 corners will have 1 by 8, 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 and at the back 1 by 8. Okay? It is not visible, 1 by 8 at the back. But this one will have total 1 contribution, which is inside body. So total contribution will be 1 by 8 from 8 corners, that is 1. So corners will have contribution 1, but inside body there is just 1 hole inside the body. So total contribution will be 2 atoms in body centered. That's what we talked about in previous class as well. Mahak, we will do the question there. I'll repeat the definition of lattice point again, okay? So in a body-centered cubic, and this will be written as BCC. Normally, you will not get in your question paper written as body-centered cubic. It might be, but most of the times BCC. 8 corners, 1 by 8 contribution of the corner, total 1. 1 at body center, 1 into 1, 1. So total 2 atoms. Sometimes reverse will also be required. It will be given that total contribution is 2. What type of unit cell it is, okay, or closed packing it is. So this is BCC. Next, face-centered cubic cell, which normally you will get written as FCC, face-centered cubic. So remember, we are talking about cubic cells. Mostly, we will be talking about cubic cells. We will not be talking about much about hexagonal, rhombohedral, tetragonal, etc. So here, what will be there? The contribution from the corners will be 1 by 8 from all corners, but at the face, the contribution is half in left side cell and half in right side cell. So one atom is actually divided in half if it is on face. And there are total 6 faces in a cube. The total contribution will be 6 multiplied by half, that is 3. So this is from faces only. Don't think that there will be only 3. There will be actually total 4 because corners will anyway be there. So what we will say, 8 corner atoms, 1 by 8 contribution, 1 atom from corners in total. 6 faces, 1 by 2 contribution, 6 into 1 by 2, 3 atoms. Total will be 1 plus 3, 4 atoms. So it means FCC will be much denser than BCC because here it is effectively 4 atoms in one unit cell. Now the question, give the significance of a lattice point. So I talked about it. The lattice point is basically represents one constant particle. One constant particle means it can be atom, ion, molecule of a solid, which may be an atom, molecule, or an ion. Just memorize this definition. You usually get this question in 1 mark. The significance of a lattice point is that each lattice point represents one constant particle of a solid. Represents one constant particle of a solid. This statement, just you need to remember. Rest you can write. Lattice point represents one constant particle of a solid, which may be an ion, molecule, or atom. Next question. Name the parameters that characterize a unit cell. This is something I need answer from you. Tell me the answer. I have not checked how many of you have submitted the assignment. I hope everyone has already submitted. Tuhina, correct answer. Don't try to write special characters, okay? As Tuhina has written, that's something you have to write. Tuhina, don't respond to everyone. Everyone has seen your answer. Just respond to me. Ashi, correct. Correct. So 6 parameters are sides and angles. 3 sides A, B, C. 3 angles alpha, beta, gamma. Three sides or edges A, B, C. 3 angles alpha, beta, gamma. Alpha is between B and C edges. Beta is between A and C edges. Gamma is between A and B edges, opposite edges. Okay. Means alpha is opposite to edge A. Beta is opposite to edge B. Gamma is opposite to edge C. Next question. Distinguish between hexagonal and monoclinic unit cell. If you remember, I said that hexagonal and monoclinic are most important ones. You will memorize all, right? Question can be from anywhere, anywhere. But the chances of these two are higher. You just need to write the configuration. And if you want to draw, you can draw the rough diagram only. So hexagonal, you know, A and B were equal because regular hexagonal base was formed. That's why A and B will be equal. But C was not equal because here it was height of the diagram hexanoid basically. Then alpha equals to beta equals to 90 degree. These two angles are equal. But gamma is 120 degrees. This is what you need to write, nothing else. Even if you don't draw the diagram, you will get the marks. Yes, Vanna, that is good, correct. So Deepa, correct. You need to write hexagonal A is equal to B, but not equal to C. Yes, Sudeepa, that is correct. Good. But in monoclinic, compare it with the last one. Okay. Remember the last one, triclinic. Nothing equal, nothing, not no angle 90 degree. Triclinic is easy to remember. From that, move to monoclinic. Side, same thing, nothing equal. But beta is not 90 degree. It means alpha and gamma equals to 90 degree. Diagram is just for clarification. Even if you don't draw the diagram, you will get full marks. You need to remember the configurations only. Next question. Distinguish between face-centered and end-centered unit cell. Face-centered means all faces. End-centered means ends. And what are two ends? Opposite. It means opposite faces. And remember how to remember end-centered. If I say this is a line, what are the ends? Ends are A and B. Similar is the case here also. If you have a unit cell, then the ends means opposite faces. Compare it with a line. Now these two faces can be any. These can be left, right, these can be top, bottom, or these can be front, back. But it is easier to show left and right. So that's why we normally show left and right. In diagrams, top and bottom very common. Yeah, because that is also very easy to show top. So you will say in face-centered unit cell, the constant particles are present in all corners and one at center of each face. Face-centered means all faces. So one at the center of each face, all six faces. This is the cross-sectional view, which makes it more clear. Yes, Prita. And OA will be 4, correct. Now, end-centered unit cell. An end-centered unit cell contains particles at corners as usual and one at the center of any two opposite faces. Say top, bottom. Next question. Is that clear now to everyone? Mm, yeah, fine. Next question. Explain how much portion of an atom located at corner, and in second case, body center of a cubic cell is part of its neighboring unit cell. A question is very tricky, and remember, you need to just think and read the question again. Question is explain how much portion of an atom located at corner. So first, don't read the second point. Yeah, just see, this is not the part. Okay, first one. Question is explain how much portion of an atom located at corner of a cubic cell is part of its neighboring unit cell. Okay, good, good, good. Uh, Rita correct, Shivangi correct, Ashi correct, Vanna correct, Rita correct, Sohani correct, Ashi correct, Tuhina, Tuhina correct, good. Yes, that one also correct. Mehak correct, Sneha correct, good. Now tell me the B part. First part, yes, your answer is correct. Now tell me B part. Now it's not there. Read it like explain how much portion of an atom located at body center of a cubic cell is part of its neighboring unit cell. Tell me the answer. Mehak, correct answer. Swangi, correct answer. Tohani, think again. Vandana, think again. Sudeepta, no. Tuhina, no. Arohi, no. The question is body center. The atom located at body center. Preeta, no. Tuhina, correct. Suhani, correct now. Good. If you have the unit cell, say this one, okay? And this one is another unit cell. And the question is, the atom present in the body of one unit cell is part of adjacent, means neighboring means adjacent unit cell. Zero. This is present in first unit cell. No part of it is present in its neighboring unit cell, whether it is on left, right, top, bottom, whatever. So the answer will be no part. Okay? No portion. Here it is 1 by 8 correct. Because if it is like this, it will be 1 by 8 in one unit cell, 1 by 8 in another unit cell, 1 by 8 in another unit cell. So there will be 7 neighboring cells total. Okay. So the corner one correct. 1 by 8 by E all 7. 7 unit cells, neighboring unit cells, and each will share 1 by 8, 1 by 8, 1 by 8. But in case of body center, no part will be in neighboring cell. Yes. Good evening, Shashwat. Okay. So the first answer is correct, 1 by 8. The second one is not shared by its neighboring unit cell at all. The answer is anyway 0. Okay. The last statement was not correct there. Now, the summary. The contribution by a particle on corners is 1 by 8. On face, half. Within the body, 1. And one more, edges, which I have not talked about, is 1 by 4. Why? Because if it is on edge, suppose suppose we have this type of, there are 4 cells. Yeah, 4 cells. If an atom is here, on edge, it will be shared by 4 unit cells. Okay, 1, 2, 3, 4. All these will have one edge common. So if the atom is on edge, it will be shared by 4 unit cells. So its contribution will be 1 by 4. In one cell, it will effectively be only 1 by 4th of its whole part. So you need to remember the contribution, if it is on edge, will be 1 by 4. Not other questions will be there on edge, based on edge, but the questions might be related to contribution only. So that's why I have included it here only. Not other questions will be on edges. Now the question. Okay, and these type of questions I'll do later on also, but just a hint here. A cubic solid is made up of 2 elements, X and Y. So these type of questions are very common in your examination. Okay, so the information will be given about whether the atoms are on body centered, on corner, and you will be asked to calculate or find the formula of the compound. Okay? So you will find effectively how many X are there, how many Y there, and then you will calculate their ratio. That ratio will be formula actually. So if effectively you have one atom in a unit cell of X and 2 atoms of Y in unit cell, the formula will be X by 2. Yeah. So the question says, atoms Y are present at corners of the cube. It means Y contribution will be 1 by 8, 8 into 1 by 8, 8 corners, 1. So effectively Y will be one atom in one unit cell. And atom X at body center, X body center means effectively 1 into 1. It means the ratio is 1 is to 1. The formula of the compound will be XY. Okay. So I had already received answers from Preeta, Shashwat, Sudipta, Ashi, Suhani, Tuhina. One correct. 1 is to 1 ratio, the formula will be XY. Contribution from corner for Y, contribution from body center for X. That's the formula XY. Now the term coordination number. Coordination number is that number by which an atom is surrounded. So suppose an atom is surrounded by 8 neighboring atoms, then it will be known as 8. Coordination number will be 8. More about it, I'll talk tomorrow or in next class. By definition, you need to just remember coordination number is by how many atoms a particular atom is surrounded by. Next, closed packed structures. Let me see the time first. We have closed packing in one dimension. Obviously, we will be talking about closed packing in three dimensions. One dimension, two dimension is just for understanding the three dimension, because otherwise it becomes complex to understand the structure. Closed packing will look like this, that all atoms are placed side by side in one direction. In two dimensions, there are possibilities, different possibilities. And these different possibilities are termed as AAA and AB. Why? I'll tell you. Okay? So AAA is that if similar units, linear units, are one over the other. So if you see both look like same, so that's why if one is A, the other one will also be A. You can't differentiate one line from the other line, one row from the other row, you can't differentiate. And in this case, if you see, a square is being formed by 4 atoms, a square is being formed. Shivangi, coordination number is by how many atoms one atom is surrounded by. So if one atom is surrounded by 8 atoms, then we will say that its coordination number is 8. If it is surrounded by 6 atoms, we will say coordination number is 6. And then you got this corrected basically. I said that we will be talking about it in next class. So this is AAA. And it is a square formed here. So that's why square closed packing. Now the next one, hexagonal closed packing. And why we call it ABAB? This is that we have one line, but the other line is not just above it. The other slightly shifted such that the atom of the other one is in the groove of the first one. A groove is being formed. In this groove, the atom of the second line or row. So because this one is different from the first one, that's why it is AB. Now, if you place another one from this one, it will look like similar. These two are similar ones. Now, this one will be in groove of B, and both these are exactly one over the another. That's why A. Okay. So it is AB, AB type. And here, if you see around an atom, it is surrounded by 1, 2, 3, 4, 5, 6, and hexagon is being formed. That's why hexagonal closed packing. So remember the name, why the names are assigned as square closed packing and hexagonal closed packing. The reason is when we form just two-dimensional lattice, two-dimensional, not three-dimensional. Okay. In first case, a square is being formed. Okay, by the atoms around an atom. So this is the central atom. Around it, a square is being formed. In this case, central atom around it, hexagon is being formed. So hexagonal closed packing. We will use these two to make three-dimensional packing. Okay. So comparison wise, you need to first understand what is AA type or AAA type, AAA type. This is AB, AB type. Square, hexagon. Now, when we have understood the two-dimensional, close packing in three dimensions. And obviously, we will be using these layers now. Layers have been formed. First one is square closed pack, hexagonal closed pack. Within hexagonal closed pack, we will have covering tetrahedral voids. What are the voids and what are tetrahedral voids? We will be talking about in just few minutes if we have time. Then covering octahedral voids. Voids means gaps, means the gaps amongst the atoms, between the atoms, the free space. Then the shape of those voids, if it is tetrahedral, we will call it tetrahedral void. If octahedral, we will call it octahedral void. So this is a square closed pack. Remember, here we have kept these type of layers one over the other, exactly one over the other, means one atom is over the other atom. So we have taken these layers and we have arranged them in such a way that one layer is above the other layer and all the atoms are one over the other, exactly one over the other. And these form a cube. So it is a square closed pack created through square closed pack, but cube is being formed actually in three-dimensional. Now hexagonal. Now why I told you cube, because we will talk about the naming convention for these ones later on. Then hexagonal closed pack. In hexagonal closed pack, you remember that we talked about the layer is A, then this layer is B, then again this is A. So we have taken that type of layer and we will keep the other layer over the layer which we have considered, this one layer. And there are two possibilities how we can place the other layer over this layer. This is one of the possibilities. Are you able to see the dim atoms, the atoms shown in dim color? Here there are no atoms, okay? And now we have placed another layer over the layer which was already there. And in this case, the placement of this layer is such that the atoms actually cover the voids. Voids means gaps. Now you might see I have written T and O. When we do so, in few cases you will see this portion, you can't see through it because on the top side you have this atom. If this atom is at the top. So although the void was there, but it has been covered. I'll show you the diagram, you can understand that in. But this one, earlier you had a gap here. This is a gap. And when you placed a layer above it, then again there is no atom. So this is the gap. So you can understand these two one by one. In first case, I'm considering just one section of it, okay? Just one section. So suppose I am talking about one section, say this section, this section, and this is the atom placed over it. So three atoms, because it is symmetrical. If you can understand just one point, it is repeating everywhere. So it is something like this. There are three atoms, the blue ones at the bottom and red is at the top of it. Now, if you see it from the side, from this side, okay, it will look like this, that this atom has been placed top of it. If you place it here, what actually happens? It forms four faces. It forms four faces. One face is formed here. The other face is formed by these two. Another face is being formed by this, and another face by the topmost atom. So if you visualize it, it looks like a tetrahedron. Now I'm explaining it in that detail, but that is not required at all from answering to the questions perspective. Okay, from that perspective, you don't need that much information. This is just to visualize and to tell you that if four faces are being formed, then it will be tetrahedron. And now you might have guessed that what we call as octahedral void, there will be eight faces. And why it happens? It happens because octahedral void is being formed by these three and these three. You need to visualize it. Okay? It means octahedral void will be formed when three atoms arranged in one way and three atoms arranged in opposite way are placed one over the other. And in this case, total eight faces will be there. Now, it is slightly difficult to visualize, but if you can visualize, that's fine. If not, even then it's fine because nobody is going to ask you how. It is first face on left hand side. Okay. So it is first face on left hand side, second face on front, third face from right hand side. So I'm considering only the front ones, front faces, the dark lines only. Then consider the back. On the back side, you have this face, back side. Fourth face. Then you have on the back side this face. Fifth face. Then you have on the back side this face. Sixth face. And then you have top and bottom. Total eight faces. That's why it is known as octahedral void. Heck, that's what I said. If you are able to visualize, that's fine. If you are not able to visualize, leave it. Nobody is going to ask you how. But if you are able to visualize, then it's fine. Yes. Similarly, here, four faces are being formed. Okay. If you understand it, if you want to, one face, if that way you want to, one face is like this. Okay. Another face will be with this one here. Another face will be like this. So three faces, vertical faces, one base, total four. So this is one face in the background, another face in the background. This one is front face, third. This one is bottom, four faces. More important for you is to understand that tetrahedral voids will have four faces, octahedral voids will have eight faces. And that too is not very important. The important thing is what I'm going to tell you. So that's why these are the tetrahedral voids formed. Okay. And you have, and this is, remember, AB, AB, and known as hexagonal closed packing. Why ABAB? Because the layers are not one over the other, and it is in magnesium and zinc. This is important to memorize. ABAB is in magnesium and zinc. ABAB HCP, magnesium and zinc. Just write it down, memorize. So I'll keep telling you from where the questions normally appear. Then you have octahedral voids. HCP is, yes, hexagonal closed packing. Hexagonal closed packing. So this was hexagonal closed packing covering tetrahedral voids. And this one we are talking about hexagonal closed packing, HCP, covering octahedral. This is ABC, ABC, and it is termed as CCP or FCC. CCP means closed cubic packing, or FCC is face centered cubic. And octahedral voids will be in ABC, ABC type. You might say, why ABC, ABC type? Because these voids will be covered only if we keep one more layer above it. Okay, one more layer above it, which covers these voids. For example, here, here, all three layers will be different. So that's why ABC, ABC. You have to cover the voids. That's so that you can have a face there. Otherwise, you won't have a face there. 8 faces have to be there. So 6 side faces will be there, but to have the top and bottom faces, you need to have the layers. What you need to remember, HCP packing covering octahedral voids will be ABC, ABC type, which is actually CCP or FCC, and examples are copper and silver. Memorize these things. One markers appear from here. ABC, ABC type, this is hexagonal close packing, which is actually CCP or FCC. FCC is also termed as CCP, closed cubic pack. Copper and silver. Now, before I move forward, just write in the chat box, what were the examples for ABAB type? Hexagonal close packing covering tetrahedral voids. What were the examples? Okay, Preeta, Shashwat, Ashish, Shwangi, good. Mehak, Arohi, Armina, Vanna, Sudipta, Yastika, good. Suhani, yes, correct. Magnesium and zinc, Mg and Zn. An octahedral void, copper and silver. Copper and silver. Now, number of voids. From here, numerical questions will appear. If the number of closed packed spheres is n, suppose you are given that, this is the lattice, this much lattice we are talking about, and in this lattice, there are n spheres and lattice points, say, okay, n spheres. Then on that basis, if no sphere is missing, no atom is missing, then octahedral voids will be same, and tetrahedral voids will be twice the number of. So octahedral voids will be same, tetrahedral voids will be twice the number of spheres or packed atoms. So this is something I have already talked about, that when we found the formula xy, I told you that x is nothing but contribution of x type of atoms in one unit cell. Y is contribution of Y type of atoms in one unit cell, and then their ratio. Now, if we know the octahedral and tetrahedral voids, we can find actually the value of n or vice versa. So these can be utilized to find the formula of compound also. But sometimes octahedral void or tetrahedral void might not have all the atoms. Octahedral voids will have some atoms and tetrahedral voids will have some atoms. Okay, so for example, if it is iron, understand why I'm talking about that. If I'm talking about an ionic solid, in ionic solid, normally anions will form the lattice. Cations are smaller. Cations will be in voids. First, you need to understand the voids are formed by the lattice points that normally anions, because anions in an ionic solid, normally anions are larger. Normally, I am saying, okay, not always. And then there will be voids. Voids will be occupied by cations. So go through it. We know that when particles are close packed, resulting in either CCP or HCP structures, CCP is FCC, okay, specifically. Two types of voids are generated. While the number of octahedral voids present in lattice is equal, means n, to the number of close packed particles, the number of tetrahedral voids is twice this number. That's something we have talked about. In ionic solids, the bigger ions, usually anions, form the closed packed structure, and the smaller ions, usually cations, occupy the voids, whether octahedral void or tetrahedral void. Then there is a rule. The rule is that normally octahedral voids are larger, and we will talk about their, the radii of the atom, maximum radius of the atom, which can be in one void. Okay, so suppose this is tetrahedral void, and I write it as TV and OV. Okay. The rule is that if the cation is small enough that it can go to tetrahedral void, then although it can go to octahedral void also, it will remain in tetrahedral void. I'm repeating. If a cation is small enough that it can fit into tetrahedral void, then although it can fit into octahedral void also, because octahedral void is larger than tetrahedral void, it will not be in octahedral void, it will remain in tetrahedral void. And the reason is that in tetrahedral void, it will be closed back. So here it is closed back. That's why it won't go into octahedral void, because there it will not fit, okay, properly. Rather, it will be loose there. If the latter ion is small enough, then tetrahedral voids are occupied. If bigger, then it goes to octahedral void. If it can't fit into tetrahedral void, only then it will go to octahedral void. Now the another point, important point. Not all octahedral or tetrahedral voids are occupied. So it is not necessary. There might be a condition that all are occupied, okay, but not a necessary condition. In a given compound, the fraction of octahedral or tetrahedral voids that are occupied depends upon the chemical formula. That actually is decided by the chemical formula, or you can say other way around, the occupancy decides the chemical formula. The occupancy of tetrahedral and octahedral voids decides the chemical formula. Now the question, yeah, and this question is easy, we have done it. A compound is formed by two elements X and Y. Y are anions, make CCP of those element X cations occupy all the octahedral voids. The concept we have already done. So I'm repeating. Anions, these form the CCP because these form the CCP means the number of lattice points will be decided by Y. And those of the element X cations occupy all the octahedral voids. So you will say suppose, assuming there are n atoms of Y, then atoms of X will be, remember X octahedral voids, 2n, there will be twice, sorry, n because this is octahedral, same number as lattice points or CCP as atoms forming CCP. This is something we are talking about. This thing. We have n atoms in closed packing. There will be n octahedral voids, and there are n octahedral voids. All octahedral voids are occupied, means there will be n atoms of X. Those of the element X occupy all the octahedral voids. So Y atoms n, X atoms n, formula XY. Ratio n is to n. That is 1 is to 1. XY. Yes, correct. Is that clear to everyone? How we found the atoms of X? Because atoms of X are in octahedral voids, we said it will be same number. Okay. So I'm going back to, okay, just to explain, I'm going back to the concept. Is this clear what I said? If in say one block say we are given, there are total n atoms which formed the lattice. Then the rule is octahedral voids will also be n and tetrahedral voids will be 2n. So this is something we need to remember. If n atoms form the lattice, there will be n octahedral voids and 2n tetrahedral voids. Now this question was that there are some y atoms which formed the lattice. The question says y type of, so y may be any element, okay? We are talking about any chemical element forming the lattice. And we assume that there are such n atoms in the lattice. Then octahedral voids will be n Tetrahedral voids will be 2n. In this question, we don't need tetrahedral voids. It is given that the X type of elements are in octahedral voids. So now there are n octahedral voids. So it means X atoms will be how many? N atoms, same, because there are n octahedral voids. All have X atoms. So there will be n X atoms. So you have Y atoms, n number, X atoms, n numbers. So ratio of X is to Y, n is to n, that is 1 is to 1, means the formula will be x1 y1, that is xy.